Hello, this is Dong-Soo from the Applied Superconductivity Lab. Today we will learn about the quench detection. In this lecture, we will cover quench detection in two sections. There are two detection methods to detect a quench before magnet damage occurs. The first method is the quench voltage detection by the bridge circuit, one of the active protection analyses. The later protection chapters will cover more details on active protection. The second method uses acoustic emission sensors to detect the acoustic signals during quench. The first quench detection method detects the quench voltage using a bridge circuit that resembles the Wheatstone bridge circuit. The bridge circuit contains two coils, L1 and L2, connected in series resistor, are representing the resistance of a small normal zone in coil 1 upon its quench, and R1 and R2, the bridge circuit resistors in which the resistances are sufficiently large. We have two governing equations. The first one is the total voltage across the two coils, VCL calculated in the direction of the red arrow. The second equation is the current through resistors R1 and R2 calculated in the direction of the second red arrow. Then, the quench voltage Vout can be calculated using these two governing equations. The important point from this equation is to keep the R of T term but cancel out the other term. As we equalize the R2 times L1 and R1 times L2, this term cancels out and only the R of T term remains. Finally, we can reduce the original Vout equation to this quench voltage detection equation. The second quench detection method is the acoustic emission technique, which uses AE sensors to detect the premature quench caused by conductor motion and epoxy fracture. Acoustic emission sensors use acoustic signals generated by mechanical vibration, and their operation principle is based on the piezoelectric effect. The sizes of AE sensors vary by their resonant frequency ranges. The below figures are based on the AE sensor experiments. First, for the conductor motion as the cause of quench, both voltage pulse and AE signal vibration were detected. Next, the system could not capture the voltage spikes for the epoxy cracking as the cause of quench, but the AE sensor captured the signal vibration. However, no voltage spikes or AE signals were detected for the critical current that caused the quench. This shows that the AE sensor may detect the quench signal caused by both the conductor motion and epoxy fracturing, which is a favorable way to indicate the pre-symptom of the premature quench. For this lecture, we have covered the quench detection methods using two different techniques: quench voltage detection by bridge circuit and premature quench detection by acoustic emission sensors. First, the bridge circuit can detect the quench by the output voltage equation when the quench occurs. Second, using the AE sensors may detect the premature quench caused by conductor motion and epoxy cracking. The significant part is that the proportional relationship between the output voltage and resistance of the bridge circuit method is critical to detecting the quench. Also, using acoustic emission signals with voltage signals may become a helpful detection method to detect the pre-symptom of quench in magnets.